Yesterday we started physics. We said physics is the study of matter and of energy and of the interaction between the two. And we said there's a whole lot of different realms of physics, anything from kinematics, which is a study of motion without regard to what causes that motion, to dynamics, which we're going to do in our next unit, which is the study of motion with regard to what causes that motion, anywhere up to atomic physics that we do at the end of Physics 30. Focusing on kinematics here, we have to know two terms, really, before we go any further, a vector and a scalar. Who remembers from yesterday what the difference between a vector and a scalar was? Somebody told me that. Somebody told me yesterday, and it might have been Jacob that told me that yesterday, was it? No? Okay, Jacob, since you got your hand up there, tell me what the difference between a vector and a scalar is. Good. It's got both magnitude and direction. Sometimes it doesn't need direction, but a vector always has direction. Sometimes a scalar is good enough for us where it has only magnitude, but sometimes we need both the magnitude and the direction. Okay? Yesterday we looked at three more terms that were examples of vectors and scalars. They were distance, position, and displacement. Who remembers what the definition for distance was? Get this one out of the way. Put your hand up and get it out of the way, because this is the easy one, right? Lewis, what's distance? Good. How far something's moved, right? How far something is moving. What's the symbol for distance? Zach, what's the symbol for distance? No, sorry. I'm looking at Aiden. Aiden. Yeah. No, careful. D or delta D. We don't want to put the little arrow over it, which means the vector, right? Because that's showing us that it's something else. Okay, we'll talk about what that something else is in just a moment here. D or delta D, either one of those is going to be fine. Okay, on your data sheet, it's got delta D. The units of distance are going to be almost always going to be, yep, good. The standard units are meters, although there will be times when we might use kilometers or centimeters, and that's okay. But the standard units, if in doubt, you're not sure if you can use another set of units, always go to meters if in doubt. Vector or scalar? We kind of already addressed this one, right? It's a scalar, right? We know it's a scalar because we don't have that half arrow over top of the D there. All right, good. Easy enough. What about position? What about position? Let's go with Carrie. Yeah, it's where something is. We always want to make sure that it's relative to something else, though, right? Okay, we say, 16 kilometers. We used that example of 16 kilometers from the Dairy Queen yesterday. It's got to be relative to something. 16 kilometers. What does that mean? The position is 16 kilometers? 16 kilometers from what? Okay, it's always got to be relative to something, and it always has to have a direction. So it's where something is, including relative to something, and including a direction. What's the symbol for position? There's only one symbol we can use here. What is it? Bart, what's the symbol for position? It's a D, yeah, almost. Yeah, with a little half arrow over top of it. And what does that half arrow mean there? Oh, Tony, I was just about to ask you, and then you put that muffin in your mouth. So I'll wait for the next question for you there, okay? What does that half arrow mean there, Seth? Yeah, it shows it's a vector. Shows that we need direction. Listen, you got a data sheet yesterday. Today we're going to learn our first equation a little bit later on. If you're ever unsure whether something's a vector or scalar, you don't remember, go to your data sheet. There's a little cheat sheet on there, right? If your data sheet has a D with a little half arrow over it, that tells you it's a vector. You don't have to necessarily remember it because your data sheet will sometimes tell you. Units are going to be meters. Of course, we just said that it's going to be a vector. Displacement. Real closely related to distance and position, but not quite the same thing. Displacement is defined as what? Let's go with Stephanie. Change in position, good. So the symbol for displacement would be what? What's the symbol for change? Symbol for change? Okay, delta is a symbol for change. Position is D with a vector. So change in position would be delta D with a vector sign over it. Good, good. Units would be meters. Okay, we didn't identify whether this is a vector or scalar yet today. But you can tell just by looking at this right now whether it's a vector or scalar. Okay, what is it? What is it, Brian? It's a vector. How do you know? You might just remember it, right? But how do you know if you don't remember? It's got the little half arrow over top of it, right? Good? So far, so good? All right. Let's introduce, let's do an example, actually. Let's do an example problem and see if we can figure out what's going on with this whole distance, position, displacement. Okay. The definitions seem to make sense to us, I think, right now. Once we start doing some examples, sometimes it gets a little bit more confusing, a little bit more muddier for a little while until we get the hang of it, and then it becomes clearer again. This example is in your textbook on page 9. Whenever we do an example like this, you don't need to copy down the example. It's in your book. Just reference it. In your notes, put example 1.1, page 9, so that you know to go back to that. What I am going to ask you to do, though, every time we do one of these examples, is to please write out the solution. The solutions are in your textbook as well. Sometimes I don't like the way they do it, though, in the textbook. I want you to write down my solution. I shouldn't say my solution, our solution, as we do it as a group. Okay? So let's take 15, 20 seconds here. Read this question. Everybody read that question yourself, and then we'll go over it. Is there anything that's confusing about that question in terms of the wording? Any words you don't know? Any words that are confusing? Any phrases that are confusing? Forget about the physics behind it right now. Just let's look at the English behind it. Is there anything that just doesn't make sense about the question itself, what they're asking? All right. Well, let's look at the physics of this question. We say a traveler is standing 1.5 meters to the right of the inukshuk. Even if you don't know what an inukshuk is, it's labeled here, right? Okay, so here's the inukshuk. We've got a traveler standing 1.5 meters to the right of the inukshuk. Tell me what this is. Tell me what that means, 1.5 meters. We've learned 3 terms so far, right? There's distance, there's position, and there's displacement. That 1.5 meters to the right of the inukshuk is what? Is it distance? Is it position? Or is it displacement? Okay, that's our first question, Stephanie. It would be position. It's where the traveler is. Now, the traveler might move, right? The position might not always be that, but that's where the position is of that traveler right now. The traveler is standing there. Where he is or where she is defined as position. So we're going to make that a D with the half arrow over, right? Not delta D. Not just D without the arrow over. This is D with the arrow over. This is position, where this person is. Oh, wait a sec. Then she moves so that she's 3.5 meters to the left of the inukshuk. What's that? Is that a distance? Is that a position? Or is that a displacement? What? Is that a displacement? Careful. That's a position too, right? This person, I think it's a girl, she hasn't moved 3.5 meters. She is 3.5 meters to the left of the inukshuk. That's where she is. That's her position. Now, I don't care that it was 1.5 meters to the right. Okay, right now, at this point of the problem, she's 3.5 meters to the left. That's a position as well. Now we have a problem. What's our problem? What's our problem? Okay, but forget about what we're asking for here right now. Let's just look at what I have written on the board here right now. What's the problem that's just arisen when I just wrote down that D? We have 2 positions. How do we solve a problem when we've got 2 things labeled the same? Okay. It's like when I have a class and there's 25 people in the class and there's 4 people with the same name. We got 4 people named Jim. Jim. Well, I've got to be able to distinguish between those Jims somehow, right? I can't just call them all Jim. I've got to distinguish between them somehow. I've got to distinguish between these guys somehow. We're going to call this guy DI and this guy DF. What does the I mean, do you think? Yeah. initial, df would mean d position final, right? So at the beginning of the problem, this was my position, di. At the end of the problem, this is my position, df. Does that make sense? So although they're both two positions, they're two different positions. So we can't call them the same thing. Here we have two girls, but they're two different girls. So we're going to call them something different, right? To distinguish between them. All right, we want to find the displacement. Displacement is d, delta d, with the arrow over it, right? It's change in position. Let's look at A. Question A here. Find the displacement. Just using directions. What do you think the displacement of this traveler is? Just using directions. Just using the fact that it's 1.5 to the right, 3.5 to the left. What's her displacement? What's her change in position? This is where she was. This is where she is now. What's the displacement there, Jared? Good. 5 meters to the displacement's a vector, right? So we need a direction for that. We're going to say it's 5 meters to the left. Does that make sense, guys? We're basically looking at this diagram that they already did us the favor of drawing out for us. And we'll look at it and saying, look, if I started here and then I ended up here, I had to go 5 meters to the left in order to get there. That works. But I'll tell you what, we're going to do this a slightly different way now that in the long run is going to end up being easier than drawing that picture out and looking at it the way that we just looked at it. We're going to use, what did I just do? We're going to use plus and minus signs here. We're going to arbitrarily define direction as being positive or negative. We're going to say here that right is positive. We could have made right negative if we wanted to, but generally we're going to make right positive or up positive or north positive. Down would be negative, or left would be negative, or south would be negative. We can define it any way we want. This is the way we usually choose to define it. Right is positive. If right is positive, then what's left? Negative, right? We don't need to write that down because we'll just assume that if right is positive, left is negative. That means that my initial position now, we're going to make my initial position not 1.5 meters to the right. We're going to make it positive 1.5 meters. My final position is going to be not 3.5 to the left, but rather, Derek? Let's make it negative 3.5 meters. Is that good? That makes sense, guys? We still haven't solved anything, right? But we've assigned directions. We've assigned signs to these positions now so that we can calculate the displacement with those signs and get a direction with it. All right. Mathematically now, displacement is change in position. The change will always be the final minus the initial. My son gets an allowance, $4 a week. Yes, so let's say he's got his allowance for the last 3 weeks. He's got $12. Okay. Saturday, he got his allowance again. Now he's got $16. What's his change in money? He has 16, he had 12. What's his change in money? He has 16, he had 12. What's his change? What's the change? $4, right? He gained $4, right? How'd you get that? You said final money minus initial money. $16 minus $12, okay? If change in money is final minus initial, then change in position or displacement is also final minus initial. Final minus initial position. The final position is negative 3.5 meters. The initial position is 1.5 meters. What's negative 3.5 subtract 1.5? Negative 5. So up here we said the answer was 5 meters to the left. Down here we're saying negative 5 meters. What does that negative 5 meters really mean? 5 meters to the, because we already defined right as positive, right? In this question, I don't know that it's any easier to do it the way we just did it using signs. But there will come a time when we get into more complicated questions where it is easier just to use positives and negatives than it is to do it this way that we did it in blue here. All right? Does that make some sense to us? All right, if you haven't copied that down, that's okay. Please do that now, though. I don't mind if you're copying while I'm writing, as long as you can focus on what I'm saying, that's fine. Okay, if you can't focus on what I'm saying, just wait, and then I'll give you a chance at the end to copy down the solution. Either way is fine, whatever works for you, okay? All right, let's take a look at these 3 questions on our own. Okay, I'll take a walk around. Stop me, please, as I'm walking around. Put up your hand. Ask me if you're struggling. Okay, read the question first before you ask me a question. Try to identify first what you have, whether it's a distance, whether it's a position, or whether it's a displacement. Okay, and then do what you do. If you're struggling with it at that point, that's the point where you stop me and ask me questions, right? Let's give it a whirl here for the next 10, 15 minutes, okay? All right, everyone, take a look up here. We're going to take a look at question number 1 here now. Everybody's read it by now, I assume. We want to find the displacement, just like we did in the example problem. We want to find the displacement, right, which is delta D with the arrow over it. But let's look at what we have here. 3 numbers, 400 meters to the north, 20 meters to the north, 100 meters to the north. Hey, the first thing I'm going to do here is just say positive is north. And then I don't have to worry about the ends anywhere. Okay, positive is north. What do I have given to me there? What is that 40 meters? Is that position? Is that distance? Is that displacement? Remember what these definitions are. Distance is how far something's gone. Position is where something is. And displacement is change in position. It's basically distance with the direction. What do we got here? Actually, it's more than distance. You could say distance is 40 meters. But you could also say the displacement is 40 meters to the north, right? Because we have a direction. 40 meters is not where the runner is. 40 meters is not where the runner is. 40 meters is the runner's change of position. Look, the runner was over here. Now the runner's over here. His position has changed by 40 meters to the north. That's a displacement. So is that. So is that. Oh, goodness. Now we got 4 different displacements. What do we do with that? Remember this, please. Displacement can be found in a couple of ways. It just depends upon what you've got given to you. Displacement in that example problem we did a few minutes ago was final minus initial position. That is absolutely a valid equation for this question, but it's not going to help me because I don't know what the position is. The displacement could also be a sum of a bunch of other displacements. So if you walk 10 meters, and then you walk 5 meters, and then you walk 5 meters more, how far did you walk total? 10 plus 5 plus 5. If we're finding displacement by positions, we subtract them. If we're finding displacement by displacements, we add them. So what we're going to do here in question number 1 is say the total displacement is 40.0 meters plus 20.0 meters plus 100.0 meters. If one of those had been south, what would we have done? If that had been 100 meters to the south, how would we have changed this? Yep. We would have just subtracted it, right? We would have made it 40 plus 20 plus negative 100. We add those up, it gives me 160 meters. I got a positive. What does that mean? Yep. North, right? We define north as positive. We got positive out of it, so it must be north. Does that make sense, guys? You're going to have to do one of two things when you're finding displacement. Subtract positions, like we did in the first example, or add displacements. You can see how critical it is to identify what you've got. Do I have positions where I am, or do I have displacements? How much my position has changed by? Zane? Well, yes, I suppose you can, but in the end, if you assume the final position is 160, like you've already added those displacements together, right? Then you've already got your answer. You don't need to subtract factor from 0. But in the end, yeah, if you said your initial position was 0 and your final position was 160, yeah, that would work. It's just that, I mean, that's an extra step you don't need to take, that's all. Does that make some sense? Okay, so try these last two questions now with that in mind. Okay, displacement is either final minus initial position, or it's the sum of all the displacements. And you've got to identify what you've got, positions and displacements. Am I going to subtract or am I going to add? Okay, we'll give you some more time to work on this. All right, everyone, let's take a look at question 2 and number 3 now. We won't always go over all 3 questions that we have as practice problems, okay? But since this is the first set we've had, since it's the first time we've done anything as a group together, I want to make sure that we're all okay with these 3 questions. Okay, even if there's ever a time when I say, let's go over number 1, and then I want to move on, if you're struggling with another one of the questions and I haven't addressed it, then stop me. Okay, I promise you. If you need a question gone over, we'll go over it. Okay? Today we're going to do it anyways. But again, if we don't do it anyways, then just let me know and we'll do it. Okay, question 2 says to perform a give and go, a basketball player fakes out the defense by moving 0.75 meters to the right, then 3.5 meters to the left. What's the player's displacement from the starting position? Clearly, we're looking for, in question number 2, we're looking for a displacement. Right? What's the displacement? What do we have here? 0.75 to the right, 3.5 meters to the left. Are those positions? Are those distance traveled? Or are those displacements? Yep. They're displacements, yeah. We know, if we're talking about distance and displacement, we know they're displacements because we have a direction, right? We know they're vectors. But we know they're not positions because it's not where the basketball player is. Listen, if I was in your spot in grade 11 for the first time, which I was in 1989, then I would make the same mistake as you guys make. Okay, going through this the first time, it's not always easy. Okay, it's hard sometimes to distinguish whether it's position or displacement. But let's just ask yourself that question. Is that basketball player, is that player 0.75 meters to the right of something? No, this is where she's gone. Her displacement is 0.75. Let's define right as positive, by the way. The displacement, the second one, is 3.5 to the left. Is that right? Is that right? What's wrong there, Alana? We're going to make it a negative, right? Yeah, we're going to make it a negative because it's to the left. Wait a second, I got 3 displacements again. What am I going to do here? I don't want to make this initial and final. I want to make this, yeah, I'm going to make it position 1, or sorry, displacement 1 and displacement 2. Okay? I don't like the whole initial final thing when we're talking about displacements because I think that just confuses us. We start mixing it up with position again. So this is the first displacement. This is the second displacement. And then as Atlanta just said, we're going to add these up. Displacement total is equal to 0.75 meters plus negative 3.50 meters. We add those together, what do we get? In the end, it ends up being subtraction, right? but we want to think of it as addition here. Ends up being negative 2.75 meters. Okay, we said negative 2.75 meters. What does that mean? What's the negative mean here? Left. If positive meant right, then negative means left. Good. Good. 3. I like this question. I like this one. While building a wall, a bricklayer sweeps the cement back and forth. If she swings her hand back and forth a distance of 1.7 meters 4 times, calculate the distance and the displacement her hand travels during that time. I'll tell you what, as much as displacement has direction, distance doesn't. Displacement sounds more complicated because it has direction. Distance sounds easier because it doesn't have direction. Let's deal with displacement first. Okay? Let's deal with displacement first. We don't know what any of the positions are here. These are all displacements. The first displacement is 1.75 meters. What's the second displacement? What's the second displacement? Brian, you looked like you were ready to raise your hand there, and then you kind of stopped. Were you? No? What's the second displacement? Someone's got to have this. Go ahead. Good. Why is it minus 1.75? Yeah, back and forth. Back. Is it 1.70? Yeah, it is. Yeah, you're right. I get too caught up in making sure I got the negatives and positives right. I missed the end digit there. 1.70 this way, 1.70 this way. We're going back and forth 4 times, though. So we've actually got 6 more displacements. D3 is 1.70. D4 is negative 1.70. D5, man, it keeps on going on forever. 1.70. D6, negative 1.70. Oh, D7, 1.70. And D8, negative 1.70 meters. Holy cow. We want to find the total displacement now. What do? Add or subtract? We want to find displacement given positions. Subtract. We want to find displacement using displacements. You add. Let's add these together. What do we get? 0. 0. Think about it. Displacement is defined as the change in position. If you go 1.7 meters back and forth, back and forth, back and forth, where do you end up? Where you started. What's your change in position then? 0. Right, you haven't changed position. When I run around the track outside, which we'll do, by the way, in cross country, so you should come to the cross country meeting tomorrow lunchtime. When I run around the track 10 times, no, let's say I run around the track 25 times. That's 10 kilometers. You run around the track 25 times, 10 kilometers. What's my displacement? 0. Because I end up where I started. Now my distance isn't 0, is it? I think you're going to find distance here. Displacement is 0. Distance is, are we going to add these up again? Sure we are. But this time we don't care about the negatives because we're looking at distances, right? 1.7 plus 1.7 plus 1.7 and so on. We add them all up, dropping the negatives because distance is a scalar, and we get 6.8 meters. When I run around the track 25 times, what's my distance traveled? 10 kilometers. What's my displacement? 0. When I drive to Edmonton and back to Okotoks again, what's my distance traveled? About 700 kilometers. What's my displacement? 350 north, 350 south. My displacement is 0. Got it? Yes? Okay, give me a second to copy those out if you don't know. I'm going to give you a few questions for homework right now that you're not going to work on right now. We're going to do another little concept here. And you probably have a little bit of time towards the end of class to work on this, but for now, we're going to say this is homework. Page 10, please do questions 1 to 7 on page 10. Homework for tomorrow.